Hello. So I'd like to provide first, as part of this module, a video to talk about the things that we did in class today, just so you have a reference to look at, and just so we can get a little more comfortable with amortized cost as a tool for analyzing algorithms. So I'm going to focus specifically on the version of this list implementation, where when I reach capacity, I immediately double the capacity and make a new array with that number of elements. And I want to think about the average number of operation per time. So what I'm going to do, and I'm going to think about the worst case. So let me think about, things double when I've added and reached capacity. So let me just think about, let me just consider adding a bunch of elements. I'm not even going to worry about removing, because removing is fast, right? So consider adding n elements. Furthermore, let's consider let's suppose that when we add the nth element, we double right at that moment. That really is the worst case, because if I just added an element and I doubled, and I'm done, then I just created all this new space and did all this work for nothing. So that's really the worst case. So let's look at that and see how it does. So what we can say is, the total amount of time. So I'll say the total time to add n elements, which is t of n. We'll call it t of n. Really consists of two parts. So the first one is the cost to change an element at a particular index in the array, right? So that happens. That happens here, right? Okay, so this is where I do the doubling, but here I do that step. Let's suppose that this takes a seconds. Okay, so that's going to contribute every time that happens. That's going to contribute some constant of a. So I don't know how long it's going to take on your computer, but let's just choose a constant that's big enough. Okay, now I need to consider the other thing, which is that the list is going to be doubling a bunch. The underlying array is going to be doubling a number of times. And so I guess to help us, this is going to be a little harder to figure out, and that's what we're going to be spending a lot of time on now. But let's assume that to create a new array and to copy in the elements. Let's say, to create a new array of size k and to copy in the elements takes b times k. All right, that's fine. So it's just some constant times the number of elements that are going to be in this new array. All right. So k is just whatever the size is going to be. So we really have to figure out. So the first part, it's not difficult to see relative to the second part that. I'm going to have to do this n times. I'm going to have to, this line of code here, where I change an element in the underlying array, is going to happen n times. So this part contributes a total of a times n time. Okay. This part may take longer. Let's see. For here, it's actually a little easier if we work backwards. So we know that. So let's work backwards. We know that the last doubling happened at n. So we actually ended up doubling up to 2n. And that took, so that would take 2n times b time, right? Because I told you that to create a new array with 2n elements, that would take b times 2n time. Okay, but before that, the second to last doubling doubled to a size of n. So that took just b times n. Then we can say the third to last doubling doubled to a size of n over 2, which took b times n over 2. And you can see where this is going, right? So dot, dot, dot. So we're going to have a sum. We're going to say, so the total contribution over all doublings is, let's just factor out the b times, okay, well, I'll write it this way first. So it's going to be 2bn plus bn plus bn over 2 plus bn over 4, all up to, you know, the initial capacity. I'll call it, I guess I'll call it n0 or something. Okay, so that's the initial capacity. All right, so this is the summation that I need to evaluate. So let me just factor a few things out here. So I can write this as, so I'm really focused on the second step here. First step we're kind of confident on that it's a times n. Second step, we got to do a little work. So let me just factor out all the 2 times n here. So we can rewrite this as 2n, and also I'll factor out the b. So 2bn times 1 plus 1/2 plus 1/4 plus 1/8 down to, okay, so let me actually, I'm going to define, so I'll call this t, it'll help if I can refer to this as a variable, t sub d. So that's the time for doubling. Okay, so that's the time for doubling. I guess I'll call this t sub a. That's the time for updating things. Okay. So the time for doubling, I'm going to call td, and we can say that the td of n is less than or equal to 2bn times all of that, actually really in the limit. So I can keep making this smaller and smaller and smaller. Eventually I'm going to reach the initial capacity and I'm done, but if I keep going, I can get smaller and smaller and smaller, and eventually I'll reach 0. And so the question is, okay, I'm summing an infinite amount of things here, turns out, because I can keep going smaller and smaller, but I'll never reach 0. But then the question is, does this converge? And it turns out this does converge. And to show you, let me draw a picture. So if I had, let's say that this was 1. Okay, this was length 1. So this is what I started to draw in class today. But Discord was not our friend, unfortunately. So if I say make this half of what it is, okay, so that's 1 plus 1/2. And then I'll have this one. Okay, so that's going to be plus 1/4. And then I'll take this one and I'll have it. So that's going to be 1/8. And I can keep going like this. I'll just draw the pictures without putting all the numbers in. So I can keep doubling like this. Or sorry, halving like this. And you know, eventually I'm going to get down to something very, very tiny. And the question is, does this converge if I add all these up? So if I put these together side by side, you can actually see that it does. So if I put this right here, and then I put this right here, and then I put this right here, and then I make one that's half. This is starting to get a little faint. Hang on one second. Yeah, and then I make one that's half of that. One second, transform, there we go. I'll put that one there, and then I make one that's half of that. I'll put that one there. And what you'll see is eventually this is going to reach the end here, but only once I do this an infinite amount of times. And you can prove this actually using limits, that this geometric series is called geometric series converges. But basically, I think I can show you with this picture here that this converges to 2. This plus all this other stuff is 1 plus 1, and actually 1 plus 1 I think we know is 2. So the identity I can use is that this whole mess actually reduces to just 2. So I can rewrite this as t sub d of n is less than or equal to 2bn times 2, also known as 4bn. Okay, 4bn. Nice. Okay, cool. So now we came up with something that looks a lot simpler, which very interesting that even in the worst case, we get a constant times n. So we really were being hard on ourselves here. We're like, look, I'm going to stop you at the worst possible time. You just double it, and I'm going to say, sorry, we're going to call it. We're done. And I'm also considering only additions, right? So the thing is only growing. So that's sort of the most I would ever have to double over some number of operations. And I still see this as a constant. Okay, so let's finish this up. So what about the total time now? Well, so the total time, Tn, that's going to be equal to the sum of the cost to update things plus the sum of the cost to double. Which that is, we can say, that is less than or equal to an plus 4bn. Oops. There we go. So what we can say, I can factor this a plus 4b out, and I can say that the total time Tn is less than or equal to a plus 4b times n. Well, I can just create a constant, c, which is equal to a plus 4b, and then I can say Tn is less than or equal to c times n. Well, now I basically can see that this implies that Tn is big O of n. Oops, sorry. I'm trying to get this all right. Is big O of n. All right. So that's cool. So interestingly, even though it seemed like, hey, the doubling was really expensive, the fact that we did the doubling led to this nice series here that we could show actually was bounded by a constant. And in the end, that meant that we could bound the entire thing by a constant times n. Okay. What this means is the amortized cost, which is the average over the n operations that it did. Remember, so the average is the total divided by the number of elements. So amortized cost, which is Tn over n, is, that would be Tn over n less than or equal to, well, just divide this by n, is less than or equal to c, right? Well, then now we can see that's O of 1. Cool. So actually, even though there's a few really, really expensive additions when I have to double the thing, on average, it comes out in the wash, which is cool. That cost that I have to pay to double the array is a good investment because there's a whole bunch of elements that I can add after that only cost 1. So that's why this is a clever scheme. All right. So hopefully that makes sense. So now we'll continue on. I'd encourage you also to look at the linked list again. So it's in our book, and I'll send the solution. But now we're going to move on to something a little different that'll get us ready for the next assignment. So we're going to talk about binary search.